And now let's start to actually use the PID controller and try to tune it and calibrate for CARLA. First, let's check the OP PID controller launch file and see what are these parameters that we can set. First parameter is stereo mode. We are using here, it shows we are selecting 1, we are using the force, the torque for steer, not the steering angle, and for the drive mode we are using the pedal stroke, rather the velocity or acceleration. For frequency, control frequency, the PID controller frequency, it is we can set the how much like each frame will take. Currently it's set for 50 Hertz, and actually it depends a lot on the input from the feedback input from the control box or the vehicle or the vehicle status we get. But once we set fixed control frequency, we shouldn't change any. We tune, and then if we change again, we need to retune and recalibrate all the parameters again. Next parameter is the engine brake acceleration, which say if we release the acceleration pedal, how much deceleration we get from the engine brakes. This could be not only engine brake for vehicle, also could be a friction or drag from the wheels, motor, wind, whatever. But it generally represents like when we don't press the brake and we don't press the acceleration, how slow, what's the deceleration the vehicle will have until stopping. Average I calculated using the manual calibration using this parameter here. I find it's around -1 meter per second square. Minimum following distance, this is used in following the next vehicle, so this is the minimum distance that we want to maintain between the ego vehicle and the follow vehicle or lead vehicle, or stopping for an obstacle, whatever. This also depends on the average deceleration for the brakes and the engine brake. We need to tune for this parameter also. But this has a relation to the OP common param, the minimum follow distance from OP common param. So we need to check and we need to maintain this should be smaller than the one from the OP common param. For higher speed we need a bigger distance. For lower speeds, of course, it's okay, we can make this smaller, depends on the agent we are running. These are the signal, the PID target signal and the PID gain. To know more about the PID controller, generally people who have experience with PID controller, they know what are these parameters mean. But if you are new to PID controller or you need to refresh your information, you can go to just PID controller wiki page. It has a lot of nice information to tell you what is the PID, the history, and also the errors you get and how to calibrate. There is several ways of calibration here. You can check, and each agent and each robot or vehicle, they have different controllers, so different response signal. So let's go back. For CARLA, the steering torque maximum 100 minus 100 left and right, and then acceleration pedal 100 and acceleration braking pedal 100. It is actually normalized from 0 to 1. I send to CARLA from 0 to 1 values for these desired signal. Of course, we can change the signal to any other signal. It doesn't have to be forced. The PID is flexible enough to handle that, but we need to tune these parameters. The PID gains: proportional, integral, and differential gain for steering, acceleration, and braking. We will check an example of tuning acceleration and braking PIDs. So first, let's see how to calibrate. Sometimes we need to know the general braking distance and the response, the values. As I explained before, OpenPlanner record a lot of information about the internal state, and especially the PID controller. Each time we run, it logs information about the general PID controller, and also for separately for each PID controller for steering, acceleration, and brake pedal. How to do that? Let's go directly to it. I will enable this manual velocity calibration. When I enable this, what happens is I don't follow the path that directly the target point. I don't try to achieve that from the global path. I just try to achieve this velocity here, and then brake to 0, and then again accelerate to this target velocity, and then brake to 0. By this, we can, for 2 iterations, we can record the behavior of the PID, acceleration, brake, PID, reaching certain velocity and braking to 0. We can repeat this experiment several times with different max velocity values. The original example, actually, I had this controller tuned with these values for running for targeting 12 meter per second velocity. So let's check what will happen if we try to calibrate with 3 meter per second velocity. So I enable this and go to save, and then run all the launch files for the AutoWare stack. It will launch, and we wait until we have localization and set goal point. Okay, now we have initial point. We set goal point. Once we set goal point, the vehicle will start moving. I try to achieve, we can see here, actually, this is the current speed. It reached the 3 meter per second and brake to 0, and then accelerate again. If we notice that there is a lot of acceleration and deceleration happening here, it's not as stable as we hope. We will see also this in the logs clearly. Now we finished our calibration test. Accelerate, and then brake, and then accelerate again to 3 meter per second, then brake to 0. Once we shut down everything, we need to actually shut down everything because the logs don't record it. They are not recorded until we turn off the nodes. It's usually recorded in the memory, and then in the shutdown in the destructor, it writes the values in the log file. Okay, let's check the log files. As we explained before, I explained this part. OpenPlanner record a lot of information in this experiment folder, and our experiment name is CARLA calibration. We go to control logs. We have log for acceleration pedal PID, braking pedal PID, control logs general one, and the follow PID for following another vehicle, and steering PID. Let's check the general control logs. You have here a lot of information which can help identify what happened in the previous test. Let's check first the current speed and the target speed. What are they look like? Okay, here we can see current speed in blue, which is obviously oscillating, going up and down, but as satisfying the stability condition for the PID, it reaches the desired target signal, which here is 3 meters per second. Then it breaks and then accelerate again, and another oscillation, and then break again. So this is not, we don't want to do this. We don't want to have this oscillation, and we can see this clearly in the acceleration signal, which the signal would we send to the acceleration. If we ride in this vehicle, it will be really uncomfortable for accelerating and braking like this, and then oscillate and then become stable. So we need to know what were the sources for this behavior. Also for this, before I move to check the internal variables for the PID, we can know the braking acceleration and average acceleration for each test by checking these values. We have here, we can see that for accelerating and braking for this one, we have average acceleration of maximum around 0.8, closer to 0.8 meter per second square, and for the deceleration we have maximum around 0.3, minus 0.3 meter per second square. This could be useful when we calibrate the, or even in the common parameter OpenPlanner, there is a variable we can set which say what is our maximum deceleration and acceleration. We can use this to handle our target velocity, the threshold for our target velocity, better than just assuming a value. Okay, let's check the internal parameters here in the acceleration. Which one component caused the oscillation? In this we can see we have logs for the proportional part, integral part, and differential part for the PID for acceleration. If we draw this, we can see obviously where things went wrong. We have a bit of oscillation in the P part, but it's not as bad as, and might be caused by this starting oscillating, the big oscillation from the differential part. If we have a look at the parameter file, before I move to that, actually we can see here there is more information. We can see the error, accumulated error, and we can compare between the output of the PID and the threshold cut from the maximum minimum values for this PID. So let's check the file again. Here the acceleration PID, we can see, wow, the gain, the differential gain is really big. What if we make that 3 or 2, whatever, like smaller value, and run our test again and check? This is how PIDs is tuned. Actually, you do initial parameters and try to check if you have overshooting. You maybe that the D component or the P component have the problem. If you are not reaching the target point, maybe your integral part is small. If you are oscillating, maybe reason because the PID is big, the P component is big, or the D component is big. If you have experience with control theory, you can understand deeper why your values, your parameter values, cause this kind of output behavior. So let's try this one and run, save, and run our experiment once more. Okay, we wait for localization. okay, we have localization and we set goal point. Once we set goal point, the vehicle will start accelerating. We can check on the UI provided with CARLA that actually it's much more stable. We don't have very high and very low throttle stroke as before, but it takes longer to reach target velocity. Still trying to reach the target velocity for 3 meters per second. Then once it reaches it, it brakes to 0 and then accelerate again. Start accelerating again to reach to repeat the cycle to reach the 3 meters per second target velocity. We can see it is smoother here, and reach velocity and brake to 0. We turn off everything and go back to our logs. We have another set of logs. From the timestamp we can know which one. Usually latest will be the it's if you sort by name, it will be next. So let's check the controller logs and check speed versus target speed. As we can see, it's much better now. We have smoother, only hesitation here, and achieve stability, and brake and achieve stability. We can check also the pedals for acceleration and brake. And see, we can see we have a bit of oscillation in the acceleration here and here. We can fix that by decreasing either the integral part or the proportional part. So as you can see, we improved the tuning a bit. We can also check the acceleration and deceleration for this experiment to see we around minus 0.1 for deceleration, and the acceleration went to 1.15, between 0.1 and 0.15. So this is like we did one experiment with the target velocity of 3 meters per second. We can do higher velocity and check the results, and we can do the same for the braking. We can check the brakes also and improve the tune the parameters, and same for the steering. Of course, steering will need a different kind of map. This map has only like 90 degrees turns and straight lines. To tune, we need to check for higher velocity and maybe some curves, continuous curves, long curves, short curves, to check the steering PID. This is a simple PID, so don't expect you get a really good smooth for all the time. You need a feed forward PID, and also you need to activate the maybe use high frequency blocker filter, frequency filter to filter the unwanted steering frequency, so you don't have your steering shaking in front of the driver. That's I think that's all. We show example of calibrating and understanding the PID parameter and using this. Once we want to run full example, we don't need this anymore. We set it to false and we save. Now we can run to reach the target point, accelerate and brake, reaching target point with the current tuned parameter. Let's wait for, okay, we have localization, then we set goal point, we find it's accelerating. Target velocity here, it's around 12 meter per second, so it try to reach that and try to maintain that. If you can see, there is some like oscillation when it reached the target. That's why the D were higher than usual. Then it reached the end, and it seems we lost localization. That's why this happened. This happened from time to time. We lose localization, and we can lose the velocity will change, and of course the controller will not be able to do. So this can be solved in other module in the AutoWare stack. The monitor can monitor that and just block, send 0 or send more reasonable velocity to the controller. So this is not a big problem. If we have continuous localization, then this will work fine as the examples 1 and 2. So with this I finished showing how to calibrate and how to use the OpenPID controller. Hope that's enough, and if you have more questions, please send to the through GitLab, GitHub or YouTube channel. Thank you very much, and see you.